our work on code instrumentation that we do in the exaFOAM project. We, as myself, Sebastian Kreutzer, and my colleague Christian Iwanski from TU Darmstadt. And yeah, quick outline. So I want to talk a little bit about our role in the project and what code instrumentation is used for in exaFOAM. Then take a step back and properly introduce what code instrumentation means in this case. And then talk about the tools we're using, especially CaPI, and give a sort of mini tutorial on how to use it, some instructions. And also explaining what kind of performance data can be collected with that. Finally, I want to go into a new tool that we are developing for, in the context of exaFOAM, which is called CaPI, short for Compiler Assisted Performance Instrumentation, and talk about the selection technique that is used to reduce the amount of collected data, and the dynamic instrumentation, or more runtime adaptable instrumentation technique we're using in this project. So as I said, we're working on code instrumentation and as part of the work package 5, so profiling performance analysis. And our goal is to provide code instrumentation of OpenFOAM that can be used for all kinds of measurements with two main features, which is low overhead, so not much perturbation of the normal runtime, and also being able to tailor the measurement to the objective of the analysis. So to only measure the parts that are necessary, and so further reduce overhead and clutter in the collected data. So what do we use this for? There are several things that we use this analysis for. First and foremost, I would say, is the general performance profiling and analysis. So that is similar to what Marta presented with the XRay tool, just a different kind of data collection. And then also we use this data collected with instrumentation for empirical performance modeling, which can be used to predict scalability issues. And the tools this is based on is the CaPI, which is a well-established performance analysis or performance profiling tool in the HPC community, which can be used for instrumentation-based profiling and tracing. And then also, as I already introduced, the CaPI tool, which is newly developed and meant for compiler-assisted instrumentation selection, which means it helps to reduce the instrumentation to the parts that we actually care about. And it integrates with CaPI and other profiling libraries, so we can actually rely on the existing technology to do the measurements itself. So now I want to go back and for people who are not familiar with it, talk a little bit about what code instrumentation means in this context. So at least for performance profiling, the idea is to insert measurement hooks into the code. This can be done by the compilers, can be done by the user or analyst, or by a separate tool, and on different representations, so source code, binary, or in an intermediate representation. For example, in GCC and Clang, there's this flag called finstrument functions, and what it does is, let me turn on the laser pointer here. So if there's some function, and this case just called kernel, so it's any kind of computational kernel, and if you pass this function, then at the entry and exit points, the compiler will insert these profiling probes that just say, okay, here's where the function starts, here's where it ends, and these probes are then calling a measurement library, which can be CaPI or any other measurement tool, which can then collect timing statistics or more advanced information about the performance of the program. The benefits of this especially compared to other methods, for example, sampling, where you just interrupt the program at regular intervals and then examine the stack to see where you are. It's kind of efficient. So these probes don't take a lot of time, and you get explicit non-statistical data. So you measure every time the function is entered. And another thing which is nice is that there's a direct correlation to the source code. So if you use, for example, CaPI will know that this probe here was inserted at this point. So it can tell you at which line in the code the measurement was recorded. The drawback is, although the probes itself are kind of low overhead, if everything is instrumented, then it adds up and it can incur a very high overhead when everything is instrumented. So you have to kind of make sure that you measure only parts that you're interested in, and there are different ways you can achieve that. But yeah, that's an issue. So if you just instrument everything and assume that your performance data is correct and reliable, that may not be the case, because the measurement may actually perturb and sort of shift the hotspots to parts which actually are not relevant, but just inflated by the overhead from the instrumentation. So now I want to go into the CaPI tool, which is the main instrumentation tool and profiling tool we use at TU Darmstadt. To use it with OpenFOAM, it's actually quite easy. Well, you have to install it, but it's open source and available. What you need for OpenFOAM is an adjusted build configuration, because CaPI does insert these probes at compile time, which means you have to recompile once to have an instrumented version of your code. For these configurations, they are available on our GitHub repo here. So if you want to try it out, you can download that, and then you can source your current OpenFOAM installation, run the install form config script in that repo, and what it will do is create compiler configurations that insert these CaPI directives so that it will be instrumented. And it will also create this CaPI prefs file. So if you load your OpenFOAM configuration with that file, it will load a separate build, which is only used for CaPI. And of course, then you have to rebuild it once, and then you have your full instrumentation. So what can you do with that, with CaPI? So there are different modes. So once you have your open source OpenFOAM configuration sourced, you can run and profile your application. There are different modes, which is the profiling and tracing mode, and I will show how they differ and what kind of data you can collect from them. There are also other options, for example, to collect PAPI hardware performance counters, which allow, for example, the calculation of derived metrics such as the IPC or instructions per cycle, which can be useful to see if parts of the code are slow, or even to compute other performance metrics on a high level. So once you have set these variables and load your CaPI instrumentation build, you can just run the program as usual, and the results will be stored in the directory that you have passed in this CaPI experiment directory variable, or in a default folder if nothing is set. There's one issue that sometimes happens, which is that the default buffer size may not be large enough, especially if you don't filter your measurements, which can lead to SCOP aborting. And if that happens, you can increase the total memory to up to 4 gigabytes, and that will usually be enough. Although sometimes, you have to reduce the amount of data you measure in order to actually be able to process it. So I want to go into the profiling mode first. This is kind of more of a high level and less data intensive mode. So what it does, it records call path informations of all function invocations and aggregates them in a call tree. And this can be analyzed in various ways. The format used is cube by SCOP, which is also an open source format, and there are different views available and analysis tools. If you want a graphical overview, you can use cube GUI, which I think is included in SCOP, but it's open source, and it's a very nice tool to investigate this call tree. So to give an overview, left here we have this metric tree where you can see different metrics. For example, the number of visits a function has, the number of time spent in each function, and then depending on your settings, for example, also the number of cycles or instructions or bytes sent, and there can be more depending on your settings. And then here in the center, this is the main profile that was collected from the run. So, for example, you have here this main function, and this calls arglist and solve function. And you see that the metric value in front of the name at each node. And the color just means like how severe the runtime or the metric is. So in this case, for example, this arglist function, which I think is initialization, has some high overhead, or not overhead, but takes a long time. Then what you also can do is use this advisor feature in order to compute advanced metrics, for example, the parallel efficiency, which then again consists of the load balance efficiency and the communication efficiency. These are the same metrics that Marta talked about. And as you can see here, if you have the PAPI counters available, you can then let it compute the IPC. And this can help narrow down the hotspots you might want to investigate. Just 1 second, I'm going to close the door. Okay, so this is the profiling mode. Then if you want to go into more detail, there's also a tracing mode, which is sort of similar to what XRay does and Paravem. SCOP, however, does not solely track the MPI functions, but does the same thing as in the profiling. It measures all functions, which means that a lot of data is recorded, which can be nice for tracking back problems to the source code, but also means that it's a lot of data you have to work through if there's no filtering method. The advantage with this mode is that you have much more detailed data. You have this timeline up here. I should talk about the tool. So this is a tool, you generate a trace, and then you can open with your tracing tool. In this case, this is a tool called Vampire, which is a commercial tool. However, I think there are also open source alternatives. I haven't tried them out, but there should be other tools that do a similar thing. So up here, it shows sort of the timeline. In this case, you can't really see much because it's very zoomed out in the screenshot. But all these different colors are different function invocations, and the lines and points here correspond to MPI operations. So you can see which process communicates with, or how the MPI ranks communicate with each other. Then also you have this, you have several views you can use to analyze the data. For example, here you have all the call hierarchy here, starting from the main function down to the sort of leaf functions in the call graph. And so you just have a more, I would say, temporal data. However, the issue is that these traces become very large quickly. So there can be tens of gigabytes large, which can become a problem. One other thing I want to talk about is when you collect this data or collect this profiling data in particular, you can use it, or we use it in the project for a technique called empirical performance modeling with a tool called XRay. And the idea here is to sort of model the behavior of each function or of selected function to predict its scalability when scaling up to many cores. And this is done not by doing any dedicated analysis of the runtime, which can be done in, I would say, smaller codes maybe, or like for specific algorithms. But for big codes like this, it's very hard to build an analytical model. So we rely on empirical measurements to build this empirical model. And this is based on this performance model normal form. So each model function looks like this. And you have different parameters that take into account the parameter, which may be the number of processes, for example. And then based on these parameters and measurements for these parameters, which would be this f function, this normal form is fitted to find a good match for each function. And to illustrate this, we have applied this to the to a grand challenge case. And so we measured from 1 up to, I think, 64 nodes. So around, maybe it was 48 nodes. Yeah, for 48 nodes. So around 4,000 processors. And so here we measured sort of the main components, which is the main function is just accumulated all other functions. And then we have 3 different solver invocations, which take up a lot of time. And then one thing we found here is that the LES model scales really badly. In this case, you don't really need the model function to see that it's not behaving nicely, but it can help in some cases. So also another case here, this is the same case, but looking at different functions. In this case, the combustion model. And here we can see that it scales quite nicely. And also the model form is quite well suited to replicate this behavior. So for this function, we can assume that they will probably not be the limiting factor when scaling up. I talked a little bit about the overhead that can be incurred when using full instrumentation, which can be significant, so up to orders of magnitude if you're not careful. And that depends highly on the program you're running, and this may skew results. This can be reduced by creating specialized instrumentation configurations, shown in IC, which only instrument a subset of your program. And sort of the default approach, or the approach, that's kind of standard, is using a profile-guided approach. So you first make your full profile or full trace, and then you look at your profile either by hand or using a tool, and then filter out functions that produce high overheads. Oftentimes, it's functions that are very small, so do very little work, but have a high number of invocations which are responsible for the majority of the overhead. And filtering out these can help a lot. For ScoreP, there's this ScoreP score utility, which can automatically generate a filter list based on threshold values for the number of invocations, the time per invocation, and percent of buffer used for each function. And you can then pass this function into ScoreP at runtime via the ScoreP filtering file variable. And when you then redo the measurements, ScoreP will ignore these functions. So the drawback here is a little bit that it doesn't eliminate all the overhead because the instrumentation is still there. It's just that ScoreP will not. So the probe will jump into ScoreP, and ScoreP will just ignore it and not record any data. There is an option to use compile time filtering, so you can use the same filter file and recompile, but for large codes, that is not very practical. So now I want to get into this new approach we're developing, which is the compiler system performance instrumentation tool, which is another way, or a more, I would say, sophisticated way of doing the selection. So the basic idea is, instead of using the full instrumentation and then using the results from that to see what you want to measure, you're starting from the source code and running analysis on the source code, and then using input from the user in order to decide which parts should be measured in the first place. So you don't have this this necessity to first do a full profile run. And also you can select based on code features or your knowledge of the code base. And if you, for example, only want to measure one aspect of your code, for example, some linear algebra part, then this is not really possible with the profile guided selection. You would have to manually write a filter file, which is not very practical. But enough about that. So this tool has sort of two features. So on one side, there's this compiler system selection feature, which is based on the Instro approach, which is another tool that applied that, which was kind of adapted here for HPC applications. And another aspect is a selection of runtime libraries for that enable adaptable instrumentation, which means that the instrumentation itself can be changed at runtime. And this tool has different interfaces, so it's compatible for profiling and tracing with ScoreP. And we also have an extension for the TALP tool, which collects pop metrics. And we're working with Barcelona Supercomputing Center to get a selective instrumentation into XRay. So to illustrate the selection, I'll hurry up a bit. Let's look at this example where you want to record call paths that contain MPI communication, but you also want to measure functions that contain loops because they might be important kernels with at least 10 floating point operations. And you don't care about system headers or inline functions because they're usually not the user code or not important if they're inlined. So what the idea is here, you take this annotated call graph, which is a static call graph collected from your whole code base. And then you have these different modules that select parts of the code. For example, this MPI collector would collect then MPI functions, would then find call paths between main and MPI communication. And these can then be combined to build this instrumentation configuration. And in CaPI, we have a domain-specific language which can be used to express this kind of selection pipeline in a quite concise way. So in the interest of time, I won't get into it. here, but yeah, you can like import different modules for MPI, for example, and then combine these selectors in order to build your pipeline. And for OpenFOAM, for the cavity case, for example, this reduces the number of instrumented functions by 74%, which of course doesn't correlate to runtime necessarily, but I will also show the runtime numbers. So one issue with that is, so the workflow that you usually have is that you run your selection, you instrument, then you get your binary with the specialized instrumentation, you measure, you have a profile, and then you see, oh, okay, I have some things I don't want to measure because they produce too much overhead, or I have things that I want to measure which are not in the profile. So you adjust your specification, and then you have to redo it. And every time you would have to recompile, which is not practical for applications such as OpenFOAM. Also, we found that with CaPI, the runtime filtering method produced too much overhead because the probes are still in the code. So there was a need for a dynamic instrumentation capability. And this is what we have developed recently, or we have used an existing capability of the LLVM claim project, which is called XRay. This is a dynamic instrumentation feature in LLVM. What it does on a high level is inserts these no-ops sleds at function entry exit points. So it's just a bunch of inserts instead of ready-made probes. It inserts strings of operations that do nothing. And then at runtime, these no-ops can be replaced by the actual calls. So the binary is rewritten and modified in memory, and can then be adapted to your instrumentation configuration. So there was a limitation. There was no upstream support, or there is no upstream support for shared library instrumentation, which for OpenFOAM is makes it not very usable. And so we have worked on this feature, and it is available on a custom fork, and we are working on getting it into the upstream Clang version. So just to illustrate here again, this is just a part of the, so the function starts here, and then this is this no-ops sled, which was inserted. And during normal execution, it will just jump over this, so there's not really a penalty. And then if we have CaPI activated and we do the patching, we pass the SE file, and then for function selected, this will be modified. So it calls first the trampoline function, which will then interface with the XRay runtime and pass information about the function to the CaPI runtime, or directly to the measurement system you're using. So to show some overhead results, one thing that's very positive is that if you don't have these LEDs active, they don't incur any measurable overhead. So what it means that you can use one build for profiling and for production runs, at least on the cases we tested. This is the case. Then here, sorry, I should explain the plot. So we have measurements for CaPI and for the type measurement system. The line is just the baseline, so the not instrumented version. And then we have full instrumentation here and 4 different CaPI generated versions. MPI is similar as shown before, instruments in MPI call path. Kernels is also part of what was shown earlier. So detecting functions with loops in them, for example. And the coarse versions are just a variation of that. And we can see that it's quite effective to reduce the overhead. Of course, you can always take more stuff out and then have less data. But we found that in these cases, the information that was there was the important information. So in order to use CaPI, it's currently sort of it's work in progress. I would say it's usable, but it requires some setup. So for OpenFOAM, what you need is the static whole program call graph, which you can either get pre-built. So if you actually want to check it out, I can get you this call graph so you don't have to build it yourself. This takes a little bit. Or you can generate it yourself using a tool called MetaCG, which does the call graph collection. And then you need the dynamic instrumentation feature from LLVM. That means you need to compile with Clang, but you need this special compiler fork that we've developed for now, which has the shared library support. Also, there are, like for SCOP, different WMake configurations, which allow OpenFOAM to build with the right flags. And CaPI is available here on GitHub. And that's it from me. So I'm happy to take questions.
Thank you, Sebastian, for your presentation. Very interesting. Do you have any questions from the audience? Questions, remarks?